Imagine a spiral, half a mile wide, glowing a fluorescent reddish pink in the middle of the ocean. It's a temporary bloom, so bright it catches the eye of passing boats and even satellites orbiting high above the Earth. This isn't some strange natural phenomenon or an alien visitation, it's a deliberate act. This summer, about 40 miles northeast of Cape Cod, scientists are intentionally dyeing the ocean pink as part of a radical, world-changing experiment. They are testing whether we can re-engineer our planet's oceans to absorb more carbon, and, in doing so, pull humanity back from the brink of climate catastrophe. What you are witnessing is the front line of a desperate battle against time. Today, we're diving deep into one of the most ambitious and controversial ideas to save our world: hacking the ocean itself. We'll explore how scientists plan to give the ocean a giant dose of antacid to neutralize the effects of climate change, why a new carbon gold rush has private companies racing ahead with potentially risky technologies, and what this all means for the future of marine life and our planet itself. This is the story of how a pink plume in the sea could be our last best hope or a devastating mistake. The reality we face is stark and unforgiving. The world is struggling, and largely failing, to stay below the 1.5 degrees Celsius global warming threshold. This isn't just an abstract number, it's the guardrail established in the Paris Agreement to prevent the most severe, irreversible impacts of climate change, the point of no return for many ecosystems. The latest report from the Intergovernmental Panel on Climate Change, published in 2023, delivered a chilling verdict. Simply reducing our greenhouse gas emissions will not be enough. We've waited too long. The carbon we have already pumped into the atmosphere has locked in a certain amount of warming. We now have to actively and aggressively pull carbon out of the air. Adam Subhas, an associate scientist at the prestigious Woods Hole Oceanographic Institution, puts it plainly. If we really want to have a shot at mitigating the worst effects of climate change, carbon removal needs to start scaling to the point where it can supplement large-scale emissions reductions. For years, our primary focus has been on land-based solutions. We've planted billions of trees, championed regenerative agriculture to restore soils, and invested in building giant, expensive machines designed to literally vacuum carbon dioxide from the air. But what if we've been looking in the wrong place? Increasingly, researchers are turning their gaze to the largest, most powerful, and most mysterious carbon sink on our planet, the ocean. As Will Burns, co-director of the Institute for Responsible Carbon Removal, points out, looking at the oceans makes a lot of sense when it comes to carbon removal, because the oceans sequester 70 times more CO2 than terrestrial sources. The ocean is already doing the heavy lifting, absorbing about a quarter of all human-caused CO2 emissions. The question that scientists are now asking is, can we make it hold even more? This profound question is the driving force behind the Loch Ness Project, the very initiative responsible for that pink spiral in the sea. The project is pioneering a method called Ocean Alkalinity Enhancement, or OAE. The concept is surprisingly simple in principle, yet profound in its potential impact. In essence, scientists are adding alkaline substances to seawater to boost its natural ability to fight back against the acidifying effects of greenhouse gases. Subhas describes it perfectly as giving Tums for the ocean. When the ocean absorbs excess carbon dioxide from our atmosphere, a chemical reaction occurs that lowers the water's pH, making it more acidic. This process, known as ocean acidification, is disastrous for a vast array of marine life. Creatures like corals, krill, oysters, and clams struggle to build their protective calcium carbonate shells and skeletons in more acidic water. Their homes dissolve, and their bodies weaken. By adding an alkaline substance, scientists can counteract this acidity, creating a more hospitable environment. But here's the game-changing part. When the alkalinity dissolves, it reacts with the dissolved carbon dioxide in the water and converts it into bicarbonate, essentially dissolved baking soda. Subhas explains, that bicarbonate is one of the most stable forms of carbon in the ocean and can stay locked away for tens of thousands, even hundreds of thousands of years. This isn't a temporary bandage. It's a method for permanently locking carbon away on a geological timescale, taking it out of the planetary system for longer than human civilization has existed. The potential is staggering. Supas believes that, in theory, ocean alkalinity enhancement could eventually remove gigatons of carbon per year, which is precisely the scale we need to make a meaningful dent in climate change. But there's a colossal gap between potential and reality. According to Will Burns, to meet our climate targets, we need to remove between 6 and 10 gigatons of carbon from the atmosphere annually by the year 2050. He calls it a titanic task. And right now, OAE and other marine carbon removal ideas are still in their infancy. Lisa Levin, a respected oceanographer at the Scripps Institution of Oceanography, offers a sobering perspective. We're really far from having any of these technologies be mature, she warns. We're looking at a decade until any serious, large-scale marine carbon removal is going to be able to happen, or more. In the meantime, she stresses, the absolute priority remains the same. We have to reduce emissions. We cannot allow these promising but unproven future technologies to become an excuse for inaction today. This cautious, methodical pace of academic science is now colliding with a powerful, fast-moving force, the free market. As the world scrambles for climate solutions, a wave of private companies has jumped into the ocean carbon removal space, and as Adam Supas notes, it's really the private sector that's pushing the scaling of this very quickly. At least 4 companies in the United States and Canada are already piloting various OAE techniques. A California startup named Ebb Carbon recently signed a massive deal with Microsoft to remove up to 350,000 metric tons of CO2 over the next decade. Their process involves electrochemically splitting seawater into acid and alkaline streams, then returning the alkaline portion to the sea to capture carbon. In return, Microsoft buys valuable carbon removal credits to help meet its own ambitious net zero goals. A new gold rush has begun, but instead of gold, they're chasing carbon credits. The question is, are they moving too fast? If you think this race between methodical science and high-speed profit is fascinating, hit that like button, because the story gets even more complicated. Another company, Vesta, is taking a different approach called coastal carbon capture. They are grinding up a naturally occurring olive green mineral called olivine and spreading it on sandy beaches. The tides and waves then wash this mineral into the sea, where it slowly dissolves and reacts with seawater to increase alkalinity. A pilot project in Duck, North Carolina, last year estimated it would remove approximately 5,000 metric tons of carbon dioxide. But these commercial ventures are not without serious risks, prompting many scientists to urge extreme caution. For instance, the olivine used by Vesta contains trace amounts of heavy metals like nickel and chromium. Some scientists are deeply concerned that releasing large quantities of this mineral could poison local marine life, especially filter-feeding organisms at the base of the food web. There's also the worry that the ground-up mineral could cloud the water, blocking precious sunlight from reaching seagrass beds and other vital photosynthetic ecosystems. And what happens if you add too much alkalinity, too fast, in a concentrated area? Some animals might simply not be able to adjust to the rapid chemical change. This isn't the only risky idea on the table. Other proposed projects involve dumping iron into the ocean to trigger massive blooms of phytoplankton, which absorb CO2 through photosynthesis. The plan is for these microscopic plants to then die and sink to the deep ocean, taking the carbon with them. The potential downside? Uncontrolled blooms can lead to anoxia, or dead zones, as the decaying organic matter consumes all the oxygen in the water. Others are cultivating huge farms of kelp and seaweed to do the same thing. There are even more futuristic concepts, like building massive pumps for artificial downwelling to accelerate the transfer of carbon-rich surface water to the deep sea. It is this backdrop of high-stakes, high-risk commercial activity that makes the LOCNS project so critically important. The 50 tons of CO2 their experiment will remove is a tiny fraction of what companies like Ebb Carbon are promising. But, as Supas emphasizes, the goal isn't to compete on scale. The goal is to provide independent, transparent,
academic research that can guide the entire industry and ensure it doesn't cause an environmental disaster in the name of solving another one. There's a genuine concern that commercial entities, driven by the lucrative voluntary carbon market, might rush into large-scale projects without conducting the necessary safety and efficacy testing.
The Loch Ness Project, funded by government and philanthropic sources like the National Oceanic and Atmospheric Administration and the Carbon to Sea Initiative, is the antidote. No carbon credits will be sold. There is no profit to be made from this experiment.
We really feel like it's necessary for the scientific community to be delivering transparent, trusted, and rigorous science to evaluate these things, Supas states, highlighting that these activities are already happening and scaling in the ocean by the private sector. Their experiment in the Wilkinson Basin is a landmark moment.
It is the first academic-only OAE experiment conducted from a ship in United States waters, and crucially, it's the first of its kind to receive a permit from the Environmental Protection Agency under the Marine Protection, Research, and Sanctuaries Act. This was no rubber stamp.
The permit was granted only after a year of intense consultations and public comment periods, where environmental groups and fisheries expressed deep concerns about everything from the critically endangered North Atlantic right whales to the larvae of commercially important squid and mackerel.
Ultimately, the EPA gave its approval, stating the small-scale project demonstrates scientific rigor and is not expected to significantly affect human health, the marine environment, or other uses of the ocean. To get to this point, the interdisciplinary Woods Hole team of chemists, biologists, engineers, and physicists spent years conducting meticulous lab trials. They tested the effects of their chosen alkaline substance, sodium hydroxide, on key local species like microbes, phytoplankton, and copepods, a vital food source for right whales. They chose sodium hydroxide, also known as lye or caustic soda, because it's incredibly pure and is already widely used to reduce acidity in drinking water systems. So, here's how the main event will unfold. A research vessel will release 50 tons of sodium hydroxide into a designated area of the Wilkinson Basin. Along with it, they will release that non-toxic fluorescent red water tracer dye called rhodamine. The vessel's own wake will help mix the solution with seawater, and after about an hour, it will form that pinkish patch visible from space. For the next week, it's all hands on deck. Scientists aboard 2 research vessels will work in rotating shifts, 24 hours a day. They will deploy a fleet of technologies, including drones from the air and autonomous underwater vehicles, to analyze over 20 different types of samples. They'll track every conceivable change: ocean chemistry, nutrient levels, plankton population health, water clarity, acidity, and most importantly, the rate at which dissolved CO2 is being absorbed from the atmosphere. They even have a protected species observer on board, with the authority to halt the entire experiment if marine mammals are spotted nearby. Yet, skepticism, even within the scientific community, remains palpable. Lisa Levin of Scripps isn't convinced the ocean will ever be a really large part of the carbon removal solution, though she sees some potential in using the seabed for storage, for example, by injecting captured carbon into basalt rock formations. Her deepest concern is our profound lack of knowledge. I am concerned about how many field trials would be required to actually understand what would happen, she says, and whether we could truly understand the environmental risk of a fully scaled-up operation. The future of our oceans hangs in the balance, with brilliant minds pulling in different directions. To follow how this incredible story unfolds and to understand the stakes, make sure you're subscribed so you don't miss our future updates. The team has already completed a full-scale dry run on a naval base, proving they can safely deliver the alkalinity. Now comes the real test in the open ocean. Preliminary results on the carbon uptake and any observed environmental impacts are expected early next year. This single experiment won't solve the climate crisis, but it represents something vital, a commitment to moving forward with caution, curiosity, and a profound sense of responsibility. As a new industry rushes to monetize the climate crisis, the scientists aboard the Loch Ness vessels are trying to write the rules of engagement, guided by data, not dollars.
The answer to our climate future may very well be written in a fleeting
pink spiral in the cold waters of the Gulf of